podcast is brought to you by LMU Munich.
Thanks a lot. I would like to thank the organizers for inviting me. I'm very happy to be here in Munich. I will be talking about the black hole information paradox, and as you see from the title, I'm going to emphasize the connection between this paradox and what happens to an observer falling through the horizon of a black hole. So the motivation for my talk is that, first of all, we would like to understand the information paradox, which is a fundamental conflict between general relativity and quantum mechanics. I will review it today. I will emphasize the paradox in flat space today. And tomorrow I will also talk about the version of the paradox in ADS. And then I will, as I said, I will emphasize that this question is related to the question of what happens to an observer falling through the horizon of a black hole. In particular, the question here is, of course, when the observer falls into the black hole, eventually he will fall into the singularity and where the curvature blows up. But the question we're asking here is whether the horizon is smooth. So according to classical GR, if a black hole is big enough, the horizon is a smooth region of space-time. You can compute the curvature on the horizon, and if a black hole is very massive, the curvature is very low. So locally, the space-time is flat. So according to classical GR, we have no doubt that the horizon should be smooth. But I will present some arguments based on quantum mechanics today, which indicate that this may not be the case. Now, the reason that we are asking this question is not only in order to understand black holes, but more generally, these questions may give us some information about principles of quantum gravity. For example, we will discuss the role of locality in quantum gravity and the extent to which it is not an exact property. And these lessons that we learn from studying black holes and quantum information may be applicable to quantum gravity in general, and also they may help us in understanding, in developing a theory of de Sitter, for example, at the quantum level, where again we have a horizon. So it could be that some insights that we gain from studying the black hole horizon may be helpful in understanding de Sitter. I won't have anything useful to say, I'm just pointing it out as a possibility. And finally, there is a more technical and concrete problem, which is that even though ADS-CFT has been very successful in proving that the black hole evaporation is unitary and allowing us to compute the entropy of a black hole, there are some open questions regarding how we describe the black hole interior in ADS-CFT. And this is a question that we want to understand, because if we could describe the black hole interior from the point of view of the dual conformal theory in ADS-CFT, we could try to ask questions about the singularity. And also, as you probably know, black holes in ADS-CFT are related to thermal states on the boundary. So some of these properties about the black hole interior may be relevant for the study of thermalization in strongly coupled gauge theories. So there may be various applications of understanding the black hole interior in ADS-CFT. So the plan of my talk was to spend the first lecture on giving an outline of the information paradox in flat space, then moving on to the paradox in ADS and presenting some proposals about describing the interior of the black hole in ADS-CFT. And in the last lecture, I was planning to talk about some more recent developments, in particular about traversable wormholes and some applications. But please give me feedback during the lecture and ask questions so that I can understand if I should speed up or slow down. And well, we don't have to cover everything. If you want me to slow down, I can just cover the first two parts and skip the wormhole discussion. All right, so now I will start by reminding you what is the information paradox in flat space. So Lars already explained that we can consider a black hole, a star, a spherically symmetric star, which undergoes gravitational collapse and forms a black hole. So we start with a star of mass m, we assume that it's spherically symmetric, and the collapse is spherically symmetric, so we end up with a spherically symmetric black hole. So the exterior of the space-time, this region, is described by the Schwarzschild geometry. In the interior, we have to know the details of the star, but we're not going to make any statement about what happens here. And as Lars explained, what Hawking found by considering quantum fields propagating on this geometry is that you have particle production in the future null infinity. So just to give you a brief review of how the calculation goes, you can take as a toy model, you can take a scalar field, a massless scalar field, propagating on this geometry, and you can expand the fields in modes. And there are two natural sets of modes. There is a set of modes which is relevant for an observer sitting in the past null infinity. So here we have modes coming in from past null infinity, and the field phi can be expanded schematically as a sum over creation operators times the wave functions relevant for this observer plus complex conjugate. But there is another expansion which is relevant for what happens at late times, where we have modes going towards future null infinity, but we also have modes going into the horizon. So these modes we call B and B dagger, and this we call C dagger. And again, you can expand the same field, the same quantum field in these modes. Well, I'm being very schematic. So this sum runs over all possible wave functions. So this is characterized by the angular momentum of the mode and the frequency. Similar for this guy. And now the point is that we have one and the same quantum field expanded in two different bases. So of course you should be able to express the wave functions which are relevant for what happens at early times in terms of wave functions relevant for what happens near the horizon at late times, right? And so you can find a relationship between these wave functions, f, g, and h, which also allows you to find a relationship between the operators that multiply the wave functions. So if you have questions, I can explain in more detail, but by comparing these two expansions, it is possible to express these modes, these operators, in terms of A and A dagger. I think Lars will explain it in more detail this afternoon, how this is done, at least in a toy model of linear space. But for now, what we need is that if you do this calculation, if you take a solution and you try, which is outgoing here, and you try to express it in terms of modes in the past, then you find that the annihilation operator B is a linear combination with some coefficients, let me call them alpha times A plus beta times A dagger. So an annihilation operator at late times is a linear combination of creation and annihilation operators at early times. Now, why is this important? This is important because if we assume that the incoming state of the quantum field is the vacuum, so we assume that at early times the field phi is in the ground state, which means that A acting on this state is equal to 0. What we find is that if we take B and we act with B on the same state, we will have the annihilation operator acting on the state, which will give you 0, but you also have a creation operator. So this means that this is not equal to 0. So in particular, the incoming vacuum is not the vacuum that you would detect at a future null infinity. In other words, there are particles which are emitted at future null infinity. And what is interesting for us is to calculate the occupation level of these modes. And if you do the calculation, you find that these modes, up to some subtleties that I'm not going to get into, you find that these modes are thermally populated with a temperature T 1 over beta equal to 1 over 8 pi gm. So that's what you get by doing the computation of Hawking. And so this indicates that we have thermal flux at infinity, and as Lars explained, this thermal flux means that there is energy which is emitted at infinity, so the black hole is losing energy. There will be some slow back reaction, the black hole will shrink, and eventually it will evaporate. Yes?
So why is this, do we expect such a correlation between the modes with expanding A and B and C? I mean, if you have open systems in quantum field theory, it's not necessarily guaranteed that you have that.
Open systems?
Open systems in quantum field theory are embedded in some thermal laws, and there's some assumption.
Oh, you're asking how do I know I can express B in this way? Well, this is a Cauchy slice, right? It's not an open system. I mean, if you look at the slices, the evolution along the slices is unitary, right? There's nowhere that information can escape. So you continue following the slices. These are space-like slices, right? And eventually you consider a slice of this form. So I have not penetrated the horizon yet, right? I'm looking at this foliation where I have a space-like slice. Well, it's a null slice, but it's a Cauchy slice of space-time. And then I deform it gradually up to the point that it follows the horizon and then future null infinity. So the propagation of the quantum field from this point up to that point is not it's not open, right? Okay, so we find this thermal radiation, and as Lars explained, the black hole will lose energy and eventually it will evaporate. So the updated Penrose diagram is the following. And here we get thermal radiation. Let me be a little bit more precise what I mean by thermal radiation. You find that these modes are thermally occupied, but you also find that higher point functions, let's say 3-point functions, connected 4-point functions, and so on and so forth, are 0. So we find that 2-point functions, B dagger B, are thermally populated. And higher correlation functions between the occupation levels of these modes, if you define the connected ones, these are equal to 0. To leading order in the computational Hawking. So this means that we get particles which are thermally populated and independent. They're not correlated. There's no correlation between different particles going out. Yeah.
So that's true to leading order?
Yeah, that's true to leading order, yes. Well, the computational Hawking is a semi-classical expansion, right? So you can have quantum, let's say, loops in quantum gravity, or you can have other effects which go beyond the semi-classical expansion. So later, we will make this more precise in ADS-FT, and then these guys are going to be suppressed by 1 over n. So in the ADS-FT correspondence, the expansion parameter will be more clean, and it will be just 1 over n. Okay, so we get this radiation at infinity, and so there are some subtleties that I have skipped about gray body factors and this stuff, which is not so important for the discussion. So to simplify, I will just say that the final state, according to this computation, is characterized by a thermal density matrix at inverse temperature beta, and in particular, this is a mixed state. It's not a pure state. So according to this computation, just a second, we can imagine that the star that we started with was in a pure state psi. So according to this computation, it seems like we can start with, so in the initial state, maybe a pure state psi, and the final state seems to be mixed. And now this is in contradiction with unitary evolution in quantum mechanics, because in quantum mechanics, the quantum state at any given moment in time is given by a unitary operator acting on the state at time t, let's say time t equals 0. And in particular, if the initial state is pure, it will always remain pure. So this evolution, which is predicted by the computation of Hawking, violates unitarity. Well, that was the first diagram, right? But we said that these C modes will back react, the black hole will get smaller, and eventually it will completely evaporate, right? So if you go to this diagram, yeah, as long as these C modes exist, you're right, that there's no contradiction because there is, well, as we will explain later, you can think of this mixed state as being purified by whatever is inside the black hole. But at some point, the black hole evaporates. And after this point, there's no black hole anymore. So there are no C modes. You just have flat space and the outgoing Hawking radiation, nothing else. Was there another question? Yeah.
So I'm wondering how exactly you take into account the back reaction. So if I understand correctly, Hawking's calculation is on a fixed background. So Hawking's so the calculation itself, that you relate A and B's, does not take into account back reaction. And then only afterwards you say you want to conserve energy, right?
Yes.
And then, strictly speaking, you already know that the final state will, so the black hole becomes something of a smaller mass.
Yes.
You know it's still a black hole. It's still an exact black hole.
Well, near the end point of the evaporation, I don't know anymore, right?
No, but also after half the evaporation, so when a significant amount of mass has disappeared, then you know that you have an object of a smaller mass, but how do you know it's a black hole?
Well, I don't know if you can do this calculation in a controlled way. I mean, you can compute the stress tensor here, the induced stress tensor, and it turns out to be negative, which indicates that the black hole will be shrinking. But to be honest, I'm not sure if this is a completely reliable computation over a long time scale. That you want to know what happens between m and m over 2, for example, right? Yeah.
It can be done in a controlled way in these 2D models.
Okay.
So if you take the module corrected CGHS model,
Yeah.
you can actually solve that and very easily check that you actually have semi-classical geometry that's perfectly smooth.
Yeah. So in 4 dimensions, I don't know it can be done. So, right, so here's the problem. It seems that we start with a pure state and we end up with a mixed state. And that is in contradiction with unitarity in quantum mechanics. So that's already a very big problem. Another intuitive way to think about it is that the final state is only characterized by the temperature beta, which depends on the mass of the initial state. So it seems that the final state only knows about the mass of the initial state. So you can have many possible initial states giving you the same final state, which indicates that we're losing information or we're losing reversibility in physics, right? We can have many different initial states giving you the same final state. Now, let me try to give you one more argument why there's a problem with this, the computation of Hawking. And I will do it here. So I'm going to consider the entanglement entropy of the Hawking radiation. To be more precise, what I mean by this is I will consider the von Neumann entropy of the Hawking radiation, which I will define as follows. So suppose we have this black hole and it emits a very large number of particles. We consider n particles or n modes and we construct the reduced density matrix for the n particles, and then we calculate the von Neumann entropy of this density matrix. Now, do you want me to remind you what is a reduced density matrix or von Neumann entropy? Are there any questions about this, or should I move on? If the state is pure, this has to be equal to 0. If this is not equal to 0, it means that the state is not pure, right? So before we argued that if you look at one particular mode of the Hawking radiation, it is thermally populated. So this means that if we consider only one of these particles, it will have a non-zero entanglement entropy, von Neumann entropy, and in particular, this von Neumann entropy will be a number which is order 1. Now, the detailed, if you want to calculate it, you have to consider a mode with frequency omega. You thermally populate it at temperature beta, and you can easily calculate the entanglement entropy for one mode. Now, if we consider two modes, each one of them will be thermally populated, and moreover, we argued that there are no correlations between them to leading order in the Hawking computation, which means that there is no entanglement between these modes, and then you can check that the entanglement entropy of two of them is simply going to be proportional to two times the von Neumann entropy of one of them. And following this argument, and to the extent that we can trust this result, what we get is that if we have n particles, the entanglement entropy will be n times this basic entanglement entropy of one of them. So then, if we plot the entanglement entropy of the Hawking radiation as a function of the number of particles, we get this curve. So this is the entanglement entropy of the Hawking radiation as a function of the number of particles. What you find is that according to the computation of Hawking, it seems to grow linearly with the number of particles, or with the number of modes that you consider. Now, at some point, well, the black hole evaporates. So, and you can estimate that the number of particles is of the order of the black hole entropy. So according to the computation of Hawking, after the black hole evaporates, the Hawking radiation has a huge amount of entanglement entropy. But then you can ask, what is it entangled with? The black hole is gone, right? There's nothing left. So this is the paradox, that you start with a state which has zero entanglement entropy, and you end up with a state which has non-zero entanglement entropy, which indicates that the state is not pure. However, this thinking about the paradox in this way also is useful because it clarifies a little bit what happens with this little corner where we cannot trust the approximations. So as Lars explained, we have the paradox even before we get to the point where the black hole becomes of Planckian size. And the reason is that at any given, so as the black hole emits more particles, it gets smaller, right? And we know that the entropy of a black hole is given by the area of the horizon. So this quantity indicates what is the size of the Hilbert space that you should associate to a black hole. So as the black hole gets smaller, the size of the Hilbert space of the black hole gets smaller because the area decreases, right? Now, if you have the Hawking radiation, which has a very large amount of entanglement, and you have the remaining black hole, which is small, it's no longer possible for this black hole to purify, to be entangled with the radiation with entanglement entropy SEE if the entanglement entropy is greater than the black hole entropy. So once this happens, then we already have a paradox. And this inequality is violated not at the end point of the evaporation, but earlier, where the black hole is still macroscopic and we can trust the computation of Hawking. So even if something dramatic happens near the last stages of the black hole evaporation, we already have a paradox before that point. Yes?
Did you start with the pure state?
Yes.
What is the whole Hilbert space you are considering?
I think that's a bit difficult to estimate because we're in flat space. The black hole evaporates, so there's an infinite volume, right? So in principle, the Hilbert space is infinite, right? So the argument I made was not about the total Hilbert space of the theory of quantum gravity, right? It was about the Hilbert space which we associate with the black hole, which we think has a dimension whose logarithm is given by this formula.
But if you start, as long as you start with the pure state and do calculations on this Hilbert space, you have to always have entanglement entropy of one part equal to the complement. And what you're showing here does not have such a problem.
Well, let me say again what I was trying to say. If you are, let's say, at this point, the black hole is still macroscopic. It's big enough so you can trust the semi-classical approximation, right? But you have a huge amount of entanglement entropy in the Hawking radiation, right? Now, if you want to demand that the entire state is pure, then these particles, the Hawking particles, would have to be entangled with a remaining black hole, right? But the Hilbert space of this remaining black hole is not big enough to accommodate all this entanglement if this equation is true. Yes?
Why don't you start with the pure state?
Well, I want to make the paradox as sharp as possible, right? I could have started with a mixed state, but, I'm trying to find a paradox, so this is the easiest way to phrase a paradox. You could have started with a mixed state, and again, you would have a paradox. Yes?
So you seem to be indicating that I can think of this label n as somehow similar to time?
Yes, roughly speaking. Maybe they're not proportional, but in some sense you can think of it as time. So this observer is sitting at infinity and keeps collecting modes or particles as they come in. So as time passes and increases, you can calculate how they're related, but
But the way you drew the diagram, it kind of seems like all of these B modes are already defined as time equals infinity.
well, you can divide along the null parameter, right? You can divide the square plus in so you can consider the number of particles which are associated with this region, then this region, then this region, and so on and so forth. Yeah.
Would the argument be still true if the higher correlations receive some corrections or some leading corrections?
No, the argument would not be true, and we will come to this point in a little bit. If this guy is becoming important at some point, then this equation may be wrong, may be corrected significantly, and then this curve will be modified. But I will discuss.
As long as the curve is monotonic in a way, is the argument still true?
Well, if the curve is monotonic, then we have a problem, right? Because in the beginning it increases, and if we want the final state to be pure, it has to go to 0. So if we want to save unitarity, then this curve has to be modified in some way so that the final point is there,
That's
right?
what I mean, but suppose it increases, as you say, maybe with some different slope or so, then there's still a paradox, right?
Yes, yeah. Okay, so we formulated the paradox in a very basic way by considering what happens to the radiation at infinity. Notice we made no reference so far about the horizon or the interior. I mean, we use the horizon to compute the flux, but after that we never said anything about what happens near the horizon. We didn't say anything about these modes C dagger. We just claimed that they exist, but we didn't really use them. So in this way, we have formulated the paradox. We have not made use of what happens. We have not made any statement about what happens near the horizon. Right? Now, what are the possibilities here? One possibility is that we have information loss, that this is the correct result, and the final state is pure, but that seems to be very dramatic. It would violate quantum mechanics on a fundamental level. Also, from the ADS-50 correspondence, we have very strong arguments today that this is not the case, and unitarity is okay, even when a black hole evaporates. So I'm not going to consider the possibility of information loss from now on. Another possibility would be that this black hole evaporation stops at some point, and then you have something left behind, which is called a remnant. So it could be that near the end point, where we cannot no longer trust the semi-classical computation, this object stops evaporating, and it's some sort of quantum mechanical object which has a very large entropy and which is able to explain the entanglement entropy of the Hawking radiation. But this will be a bit problematic because the mass of this object would be of the order of the Planck scale, because if it was significantly heavier, then there is no reason not to trust the computation of Hawking, right? So it would have to be Planckian, but it would need to have a very large amount of entropy, or many possible internal states. And the problem is even worse because you can repeat the same argument starting with a bigger black hole in the beginning. So the initial mass of the black hole can be arbitrarily large, and what we get in this scenario of the remnants is that you always end up with a particle, or an object with small mass and entropy which is unbounded from above. So this would be very dangerous, and also from the ADS-50 correspondence, we know that these objects do not exist, at least in ADS. Yes?
There's an argument, I think, by Strominger, maybe 1 year old or so, who is saying that they are not only these Hawking modes, but additional soft modes.
Yes.
And, these soft modes are able to, so to say, to purify the state at the end. Will you come to this? Or
Yeah, I'll come to this.
Yeah.
I'll come to this in a little bit. If I forget, please remind me. Okay, so the final possibility that I will try to consider is that unitarity is okay, the black hole evaporates completely, but for some reason this curve gets modified after a certain point in such a way that you end up with a pure state. Now, to motivate this, we can ask the question, what happens if we burn a piece of paper or if we look at the radiation coming from the sun, right? So if you look at the photons coming from the sun, they seem to be in a thermal state. However, we don't worry about information loss. And the reason we don't worry about it is that when you burn a piece of paper or you look at the radiation from the sun, there are actually small correlations between the photons. So this is not exactly equal to 0. There are small correlations between the photons which are sufficient in order to restore purity, the purity of the state, and to carry away the information. So if we look at a burning piece of paper, these assumptions would be these results would be slightly modified. So you would detect thermal radiation plus small corrections. And this would not be equal to 0. There would be some small correction again. And in that situation, it is known, you can actually show it in toy models, that these small corrections are sufficient in order to modify this curve and make it look like this. So I will explain in detail, but I'm just trying to tell you where we're going to. Yes?
What is small?
I will quantify it a little bit, in a little bit. Okay, so from now on, I will consider the scenario where unitarity is restored by small corrections to the Hawking computation, right? So. So what I'm trying to quantify is what exactly do we mean by small corrections. So are these corrections small? So I will try to quantify what we mean by that. And I will try to be more precise about the class of observables that we'll be talking about. So we want to consider some corrections and quantify what we mean by small, and also make more precise the class of observables we will be talking about. Now, what I want to say with this is that, for example, if you consider the entanglement entropy of the Hawking radiation, and if you want to find a way of converting this curve, which is predicted by Hawking, to the curve that's necessary for unitarity, obviously this is a very large correction, right? So if you try to compute the corrections to the entanglement entropy of the Hawking computation, you will have a very large correction. However, as I will explain, first of all, this object is not an observable. The entanglement entropy is not something you can measure. It's not a linear operator. It's something you can compute, but you cannot measure it. So it's not really an observable. And so I will try to make a distinction between observables and things that you cannot really observe, you can compute, and I will try to quantify what is the necessary size of corrections to physical observables. Yes?
I mean, you can try to set up a system so you measure the Renyi entrophies
Yes.
directly by having multiple copies of the system. So I think in principle it's not inconceivable. I mean, you can get pretty close to measuring the entanglement entropy if you have many copies.
Pretty close, yes, that may be true. But I think you can prove that you cannot measure it exactly. So you cannot find a linear operator.
Based on the linear operator.
Right. You cannot find a linear operator that will reproduce. There must be some approximation.
Since there's always some kind of calculation that you do with your measuring. I'm just saying you can. I think you can get pretty close to measuring.
Okay.
I don't think it's a problem for
Yeah, so we want to quantify these corrections, and so we want to estimate. Right. So what we're going to do now is, of course, we will not be able to compute these corrections, right? That would be equivalent to computing the S matrix for black hole formation evaporation. That's impossible at the moment. What we're trying to do now is to estimate what is the necessary size of these corrections in order for unitarity to be restored. Now, to do that, I will review for you some basic arguments from statistical mechanics, which are rather basic, but I think it doesn't hurt to review them again. So, and I will use them a lot tomorrow, so I will review them now. So when we want to ask this question, what we're really asking is, how can we distinguish a pure state from a mixed state? Because Hawking predicts that the final state is mixed, and we want to consider a scenario where some additional effects in quantum gravity restore unitarity, right? So we want to consider the computation of Hawking. We get a mixed state. And we want to compare what we would get in a scenario where we have Hawking plus corrections, where the final state is now pure. So we want to ask, suppose you look at this radiation that you get in the calculation of Hawking, and you try to compare it to what you would get from a computation which would be unitary, and we try to quantify the difference between these two states of the radiation, right? So as I said before, what we need to study is the difference between a pure state and a mixed state. And here I will try to argue the following general statement. So in a system with many degrees of freedom, most pure states look almost the same for most observables. And almost the same as the maximally mixed state. So this is an intuitive statement that I will make more precise in a little bit. In particular, I need to quantify what I mean by most pure states, almost the same, and for most observables. But the intuition is basically that it's extremely difficult, almost impossible to distinguish a pure state from a mixed state by measuring normal observables. In other words, the expectation value of a normal observable will be almost the same in a pure state and in a mixed state. Now, I want to quantify this a bit more precisely because I'm going to use some of these inequalities or equalities tomorrow. So we're going to spend 10 minutes on this now. So we will prove a simple theorem which will tell us what is the difference in expectation values of operators in mixed states versus pure states. So let's see how we prove this. So we will assume that we have a finite dimensional Hilbert space. So we have a Hilbert space of dimension n, and we consider a basis of states, some orthonormal basis, I goes from 1 to n. So this is some particular basis of the Hilbert space, and I want to consider a very general pure state in this Hilbert space. I should not take just one of the elements of the basis. I should take an arbitrary linear combination of those. So a general pure state will have this form. Where Ci are complex numbers that have to obey the condition that sum of Ci squared is equal to 1. Yeah.
Do you need that the system is thermalizing, or you just talking about whole systems?
I'm sorry. It has to be it has to be chaotic, or yes, not ergodic. It has to be chaotic, so that I will make a statement now which will be justified if the system is thermalizing. So we consider an arbitrary pure state, and now we want to study, and we also consider an observable. A acting on this Hilbert space. I don't care what it is. It can be an arbitrary operator. I impose no conditions on this A at this point. It's an arbitrary observable, and I want to consider the expectation value of this observable A on different pure states. So I consider many different pure states of this form, and I want to see how the expectation value changes. Is it very different among different pure states? Is it almost the same? Now, of course, there will be some states where this guy has a value which is different than other states. But what I want to know is what is the expectation value for this observable on most states. So to do that, we introduce the notion of a typical pure state, which means that intuitively, it means that we select these coefficients Ci randomly, subject to the condition that the sum must be equal to 1. Now, when I say randomly, I have to be more precise and I have to define a measure. So we'll do it right now. Notice that any pure state in this Hilbert space can be written in this way, and the Ci's have to obey this condition. These Ci's are complex numbers, so you can split them into real and imaginary parts. So here you have 2n squares. And then this is the equation for a unit sphere in 2n minus 1 dimensions. So the set of all pure states in this Hilbert space can be associated to a sphere of dimensionality 2n minus 1. And now we're thinking about a macroscopic system, so this n is a huge number. So it's a sphere of very large dimension, right? So we have a sphere of all possible pure states. Any point on the sphere represents a particular pure state. Now, if I want to define a measure for these pure states, the most natural measure to define is the following. You consider the uniform measure on this sphere, and you declare that the probability to select a particular value for Ci is proportional to the volume element of this uniform measure. So if you take a region here on the sphere and you consider all possible pure states in this region, we assign the probability to this set, which is given by the volume of this region divided by the volume of the entire sphere. So this is the most natural measure, and this is also what we use in statistical mechanics. You can think of it as a microcanonical measure where every state is equally likely, right? So this is the microcanonical measure sometimes we also call it the Haar measure, because it's invariant under actions by unitaries on this sphere. And if you want, you can write it in equations as follows. This measure is some normalization, let me call it kappa, times dC1, dC1 star, dC capital N, dC capital N star, times the delta function of 1 minus sum of Ci squared. So this is a measure for pure states, right? And we select this normalization constant in such a way that the integral of d mu is equal to 1. Okay, so we introduced the notion of a typical pure state. Typical pure state means that you consider this measure and you consider a set of states which has a very large volume using this measure. So if you say property, a particular property is true for typical states, what we mean is that it's true for a volume, for a subset of this sphere which has very large volume compared to the total volume of the sphere. Now, it's also useful to introduce, these are all pure states, but it's also useful to introduce the microcanonical mixed state. So this is not the same thing, this is a mixed state. And it is defined by density matrix, which is a identity operator acting on this Hilbert space divided by n. All right, so now we have set up all the ingredients, and now I can try to prove this theorem. Yes?
Sorry, but what you call typical depends on the basis, right? So
No, it doesn't depend on the basis. It depends on the, I mean, in the beginning, I set it up using this basis, but then I defined a measure which I argued is invariant under the action of unitaries, which means that if you change the basis and you redefine the measure, it will be the same measure.
But for example, consider the state where the CIs are all equal, so that would call typical, like the order of magnitude of all CIs are equal, and then you would call typical.
No, I don't think you can take just one state and say that this state is typical. That you cannot do, right? What you can do is you can take a set of states and ask whether that set of states should be thought of as a set of typical states. One state by itself, as you said, I mean, unless I select the preferred basis, then all the states are fully equivalent. So it can't be that one is typical, the other are atypical. Yeah.
Just to be pedantic, a property could be true for some sort of interesting fractal-like structure on the sphere. You might not.
Fractal? Yeah, I guess, in principle, let me think for a second. A property. Yeah, I guess a property could be true for a fractal set, yes. Then I wouldn't know how to define the notion of typicality there. I would have to think about it. If you're asking about expectation values of observables, that I don't think can have very exotic behavior because these are linear operators. So evaluated on this stage. So that is, I will write it down now. I mean, I don't see how it can have a fractal structure. Good. So we want to consider all the states, and now we want to see how this quantity varies as you consider different states, different pure states. So let me now prove this a basic theorem. I don't know what is the earliest reference. Maybe the one I know is the PhD thesis of Seth Lloyd, but there may be some earlier reference where it has been derived. So it's very basic. But it's very useful. So the first statement is that if you consider this expectation value of A, and you take the average of this quantity over all pure states, the result is exactly equal to the microcanonical expectation value. This is an exact statement, right? There's no approximation here. How do we prove this statement? Let me prove it. This guy you can write as follows. So this is the integral over d mu of the matrix element of the operator A multiplied by Ci star times Cj, right? I mean, you take the state psi and you expand it in this basis, so you get these coefficients. Now, this guy is a matrix which does not depend on C. So I can also pull it out in front, right? So the left-hand side is equal to this quantity, right? Where I have to sum over I and j, of course. Now, let's look at this integral. This integral does not depend on observable A. It's just an integral over these C's, which have to obey the condition that they lie on the sphere and they're distributed with this measure. Now, you notice this measure is invariant under rotations of the phase of the C's. So this result, this quantity should be the same if you make a change of variables where you take Ci into e to the I theta I Ci and the conjugate in the obvious way. And you can select these phases independently for each Ci. The integral, the measure should be invariant. Because if you look at the measure, you multiply C with C star in all possible ways, right? So these phases are invariant. But the integral will rotate by e to the I theta I minus theta j. So the only way that can be consistent is if the integral is equal to 0 when theta I is different from theta j. So what we learn is that this integral is actually proportional. So what we learn is that the integral d mu Ci star Cj is proportional to delta Aj. Now, how do we fix the constant of proportionality? Well, when I is equal to j, what we need to compute is the integral of d mu Ci squared. And you also notice that this integral is invariant under permutations of this I. There's nothing special about I is equal to 1, 2, or 3, right? You can interchange them. So this integral is actually independent of I. And you also have the condition that the sum of Ci squared is equal to 1, which you can put inside the integral. And basically, you can determine that the constant of proportionality is 1 over n. Okay. Okay, so we found that this integral here can be written as 1 over n aij delta ij, which is the same thing as the trace of rho microcanonical times a. So we proved this theorem. It was very simple. So what does it tell us physically? It's telling us that if you look at all possible pure states and you take the average of the expectation value of A, you will recover the expectation value in the mixed state. Now, this by itself is not telling you that a typical pure state will look like the mixed state. Because so if we, for example, if we make a cartoon of all possible pure states psi, here we have the expectation value of the microcanonical state, the mixed state, and on the vertical axis we plot the expectation value in a pure state. What this part of the theorem is telling us is that every different pure state will have a different expectation value, and if you take the average over all of them, you will recover this line. But it doesn't tell you how far pure states are compared to the microcanonical mixed state. It could be that these fluctuations are large, or it could be that these fluctuations are small. So to answer that question, we need to go one step further and compute the variance of this quantity, right? So we need to do an integral which is a little bit more complicated, and I will write down the result without proving it, and that will be the more powerful part of the theorem. If you compute the integral over all possible pure states of the difference between the expectation value on the pure state psi minus the expectation value of the mixed state, and you square it, so this is the variance, this quantity is equal to 1 over e to the s plus 1 times the trace, times trace of rho microcanonical a squared minus trace rho microcanonical a, the whole thing squared. Okay? So this, sometimes we also write in the following way. we write this, we interpret this result as saying that for most pure states, the expectation value of A is equal to the expectation value in the macrocanonical ensemble plus exponentially small corrections. So this is less precise. This is an exact statement. Now, let's look at this again. So this is telling us if you look at all possible pure states and every time you compute the deviation from the average and you square it, the result is going to be exponentially suppressed in the entropy. Now, usually, this quantity is not too large. I will come back to this in a little bit. Just let's assume for a moment that this quantity is not too large. Then this theorem is telling you that the variance is exponentially small, which means if we go back to the previous diagram where we had the expectation value in the macrocanonical ensemble, what we find is that for most pure states, the expectation value will be really, really close. There may be some crazy states where it deviates a lot, but there will be very few of them. Now, I want to emphasize that this theorem does not depend on the Hamiltonian. I did not use the Hamiltonian of the system anywhere. It does not depend on A. A can be anything. This is just an identity in linear algebra. A can be anything, the Hamiltonian can be anything. So A can be a very complicated operator. It doesn't have to be a simple operator. If you're worried about the possibility of this guy becoming too large, I think there are two related ways to think about it. First of all, when we want to say whether the variance is large or small for an observable, we have to decide what are we comparing it to, right? Because if you take an observable A and you multiply it by 1 million, the variance will be amplified, of course, right? So it's natural to compare the variance to perhaps the norm of the operator. So, of course, if you multiply A by an arbitrary number, this will get large, but at the same time, the expectation value will get large. So you should consider some ratio. But perhaps a better way to do it is to, instead of looking at an arbitrary observable A, consider a projector, a projection operator. So any observable in quantum mechanics can be expanded in projectors. Take one of those. That guy has eigenvalues 1 and 0, right? So this quantity is bounded from above by 1. It can never get too large. So if you take projectors, if you measure a projector, you're guaranteed that the result in a pure state, in a typical pure state, is going to be exponentially close to the macrocanonical expectation value. And again, this statement does not depend on the Hamiltonian of the system or on the nature of this projector. Yeah. Yeah, that's restrictive. I mean, if you take a different one, then you have to redo the theorem. It will be so. What is relevant for us is what happens if you take the canonical density matrix, for example, right? In that case, these error terms will not be exponentially small anymore. They will be suppressed by 1 over the entropy, some power of the entropy, 1 over the entropy. So if you change the density matrix, you're right that this theorem will have to be modified. So this theorem holds only for in the way I have written it down. Yes. Yes. You have to assume that the radiation that we get from the sun can be modeled by a typical state, right? I mean, I think it sounds reasonable in the sense that the sun is a complicated system, so probably the radiation that comes to us is in a probably typical state, right? It may not be fully typical, but it depends on what you want to ask, what kind of question you want to ask later. So, sorry, I wanted to make some statements about this theorem now. Interesting. Oh, there it is. So, I don't know if Samir is here, but at some point, the discussion will come to the fuzzball proposal, which suggests that the geometry behind the horizon may depend on the microstate, right? I think for that proposal, it is interesting to consider how it can be reconciled with this theorem, which is telling you that no matter what observable you take, its variance among different microstates is going to be exponentially small. So this theorem suggests that when you're falling through the horizon, and if all these assumptions can be applied, that we have a Hilbert space, Hermitian operators, etc., this suggests that the experience should be almost the same for all black hole microstates. The variance among different black hole microstates will have to be extremely small. Now, you may think also that this theorem means that you will never be able to distinguish a particular pure state. Suppose you want to verify whether the state that you get from the Hawking radiation is a particular state psi 0. This theorem is telling you that no matter what you measure, it's going to be always the same. So how can you distinguish the state psi 0? There is an answer to that, which is the following. If you take A to be the projector psi 0, then this guy will be the expectation value of this object on most states will be exponentially small, except for the state psi 0, where it will be exactly equal to 1. So if you select the observable in a correlated way with a microstate, then you can end up in these wild fluctuations and you can detect the state. But of course, this is something very difficult because it means you must already know the state and you must design a very complicated experiment which is designed to probe this particular projector. So what I want to say is that in this theorem, we have assumed that we fix the operator and we vary the state. If you vary the state and at the same time you vary the operator in some correlated way, then you can violate this theorem. Also, this theorem does not apply to non-linear objects like the entanglement entropy, right? I mean, this is a theorem about linear operators acting on the Hilbert space. So you cannot use it in this form directly to compute, for example, the variance of the entanglement entropy among different, well, I don't know. Like, suppose you decompose the Hilbert space into two parts and want to do some statistics of the distribution of entanglement. You have to be careful how you do that because this theorem relied on the assumption that A was a linear operator. Also, another comment is that this is not saying that the observable A must have a definite, must have a small quantum variance on a state psi. This theorem is not telling you that. The variance we're computing is not the quantum variance, which is this quantity. Right? Suppose you have a state psi, and you measure A many times, you repeat the experiment many times, you will get a variance, right? In quantum mechanics, psi is not an eigenstate of A in general, right? So you will have some quantum variance. This theorem does not impose a bound on the quantum variance. This variance we're computing is a different type of variance. It's the variance among different pure states. So as we will see tomorrow maybe, if you look at the black hole in ADS and look at the quantum fields outside the black hole, the occupation level has a variance which is order 1. It's not exponentially suppressed. But if you compare this variance among different pure states, the result is going to be the same up to exponentially small corrections. In other words, this theorem is telling you that the probability distribution for A is going to be almost the same on different pure states. It's not telling you that the probability distribution is picked along a particular eigenvalue. It's just telling you that it will be similar in different pure states. Also, let me, final comment. This is not the same thing as the eigenstate thermalization hypothesis that I'm going to present later. It may sound similar, but it's not the same thing. In particular, here we have not used the Hamiltonian anywhere, or dynamics, right? The only place where we implicitly use dynamics is by, let's say, highlighting the relevance of typical states. Because if the dynamics is chaotic, then you can expect that under time evolution, the system will probe the entire Hilbert space. Okay, so now what is the relevance of this for the Hawking radiation? The relevance is that if we had a mechanism which will unitarize the radiation, what we expect on general grounds from this theorem is that, so suppose we have some, we have the Hawking effect plus corrections such that the whole thing is unitary. What we expect is that, let's say B dagger B, for instance, the expectation value is going to be thermal plus exponentially small corrections. And these correlators, B, 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 are going to be 0 plus exponentially small corrections. So really small corrections are, you can postulate some mechanism that will unitarize the radiation while at the same time maintaining the predictions of Hawking to leading order in the entropy. Now, so the Hawking computation is good for computing for you this type of observables up to very small corrections without violating unitarity. However, it's not good if you want to compute the entanglement entropy of the Hawking radiation, because we found that the entanglement entropy will need a very large correction, right? To go from the thing that Hawking computes to 0. Or if you ask the question, what is the quantum state of the field, the entire quantum state of the field at Scri plus? In the case of Hawking, it's mixed. In the case here, in this hypothetical scenario, it will be pure. So that's a big difference. But notice that this quantum state is not an observable. It's not something you observe, right? You can probe the quantum state by computing expectation values of observables, and if you perform a huge number of those experiments, you can reconstruct the quantum state, but you cannot directly measure the quantum state. Okay, are there any questions? Do I have to stop at 12:30 or?
We started 10 minutes.
Okay.
So if you set up the same black hole collapse on repeated copies and then measure different properties
Yes.
of the Hawking output state, could you definitely find out what the Hawking radiation output state would be?
Sorry, you're saying you prepare many identical stars in the exact pure state, psi, you let them collapse, and you perform a huge number of measurements on the outgoing radiation, right? Your question is, can we reconstruct the state psi? We should be able to, yes. Are you mean according to Hawking or according to? Yeah, we should be able to. So what? All right. So let's go back now to this entanglement entropy curve. So here we assume there's some effects in quantum gravity. We don't know how to calculate at the moment, but what they do is they unitarize the radiation, and we found that this can be achieved without modifying dramatically the predictions of Hawking for low point for correlation functions of the outgoing photons. Now, of the outgoing Hawking particles. Yeah. So what we expect then is that if you look at the entanglement entropy as a function of the number of particles, this is what Hawking predicts. And what we instead hope to get is something like this, right? Now, this is compatible with the idea of having small corrections because, as I already emphasized, this quantity is not an observable. It's some quantity that is very difficult to reproduce, right? And so let me now also mention a little bit the analysis of phase. So this is called the phase curve. So here the idea is that in the beginning of the black hole evaporation, the particles that get out increase the entanglement entropy of the Hawking radiation. They keep increasing it up to the midpoint of the black hole evaporation, where half of the particles have been emitted. And from that point on, what happens is that the additional particles that get out start to decrease the entanglement entropy of the Hawking radiation. So this is called the midpoint of the black hole evaporation, where half of the entropy has been emitted, is called the phase time. It's a very long time scale. It scales like m cubed, right? And then the idea is that after this point, the particles that get out have the property that they start to unitarize the outgoing radiation. Now, why did I draw it in this way? Well, this is a general question, which is the following. Suppose you have a system, a big system of many degrees of freedom, and suppose that this system is in some typical state psi. An interesting question to ask is, if I take a subsystem, and if I calculate the reduced density matrix, what does it look like? And what Page showed is that if the subsystem is small, the reduced density matrix looks maximally mixed. So it looks like the identity divided by the size of that small system. Well, if you increase this guy a little bit, this continues to be true, but of course there are always some small corrections, right? As you increase the size of this small system, these corrections become more and more important. So you can, using this analysis, you can calculate the entanglement entropy of this reduced density matrix as a function of n. And what you can easily show in toy models is that it has precisely this form. So, capital N over 2. So as you look at more and more particles in the system, in the beginning, the entanglement entropy keeps increasing. And after you reach the point where the subsystem is half the size of a big system, then the entanglement entropy starts to decrease. So the intuition here is that as we start to collect all these Hawking particles in the beginning, where we're probing a small number of these guys, the entanglement entropy will increase. And then if we start collecting more than half of those, the entanglement entropy will start to decrease again. Now, this is compatible with this theorem I mentioned before. For example, if you take only 2 particles, and you can try to reconstruct the reduced density matrix for these 2 particles by applying this theorem, and we will conclude that this reduced density matrix will have to have this form. But as you start to increase the number of particles, then you run into this issue that you're no longer computing the expectation value of some observable, but rather you're computing the entanglement entropy, which is a more complicated object, and these small corrections are able to pile up and unitarize the state. Now, there's a very simple toy model you can use to study it yourself. It only takes a couple of hours. It's just take a spin chain, take n spins, spin 1/2 particles, so they can be up or down, let's say. And you can consider a base of states of the form, 1, 0, 0, 1, 0, where 1 denotes up, 0 denotes down. And you have many of these states. So there are many of these states. There are actually 2 to the n states. And write down a random typical state, psi, which is a superposition of these guys. Select this number ci randomly, and then try to calculate the reduced density matrix of the first spin. What you will find is that for one spin, it is equal to 1/2, 0, 0, 1/2, plus exponentially small corrections, right? Then you take 2 of them, row 2, and you find that the density matrix is 1/4, 1/4, 1/4, 1/4, 0, 0, plus exponentially small. Keep doing that by considering more and more and more spins, and at some point you will see that these corrections become important, and that's precisely the point where the entanglement entropy of this subsystem starts to decrease. Another way to understand it is that if you have a big system in a pure state and you divide the 2 parts, we know that the entanglement entropy of this part is equal to the entanglement entropy of that part. So this curve has to be symmetric. Okay, so so far I have reviewed some aspects of the black hole information paradox, but if you notice, almost everything I said had to do with the properties of the radiation at infinity. I did not really say a lot of things about the horizon or the interior of the black hole. So as we will see, so this part of the paradox where you only ask the question what happens to radiation at infinity, you can imagine a solution of that paradox by postulating some additional effects in quantum gravity, which will introduce these small corrections, which will unitarize the radiation, and there's no longer any paradox, any conflict between different principles. We don't know how to calculate these corrections, but in principle they could be present, and they don't violate any other principle that we know. Now, I want to argue that the paradox becomes more sharp if we try to reconcile it with a smooth interior. Yes?
So why is it very important? Because if I think about the sun again, probably in the calculation I have to do there, the interior of the sun is not that important.
You can do this analysis for the sun. It will go through in this way, right? And there will be no paradox, so you will be happy, right? But in the case of the sun, you know that its interior is made out of stuff, right? And you don't have to reconcile this scenario with the requirement that the interior of the sun is empty, in the same way that the space-time near the horizon of a black hole is empty. So I will make give me 2 minutes and I will come back to your question. So a simple way to explain why there's a problem is the following. We consider an evaporating black hole, and we assume that the evaporation is unitary, so everything that falls into the black hole gets encoded in the Hawking radiation, right? So the quantum information of whatever fell into the black hole is coming out in the Hawking radiation. Now, suppose that we throw a qubit A into the black hole at some point, right? So the problem is that in this, so if the black hole does not destroy information, the quantum information of the qubit has to be encoded somewhere inside the Hawking radiation, right? Let me denote that B. So it will not be in a simple form. It will be scrambled with the Hawking radiation, but in principle, you should be able to reconstruct the information of this qubit if you measure this radiation, right? The problem is that in this geometry, it is possible to draw a slice, a space-like slice, which has a property. So this slice is called, it's usually called a nice slice. It has a property that it is space-like, right? It has low curvature everywhere. And it intersects, it contains the qubit A that fell into the black hole and most of the Hawking radiation, or a sufficient amount of the Hawking radiation so that you can extract the qubit B. So it contains the Hawking radiation. So in particular, it contains B. So this means that there is one moment in time, this moment. So we're in GR, right? We can select the foliation of space-time in any way we like. We don't need to use Schwarzschild time. We can foliate in this way. And then there is one moment in time, characterized by this slice, where if you consider the quantum state of the system on this slice, it contains 2 copies of the same quantum information, right? So this is not consistent with linearity in quantum mechanics, and in particular, this would result in quantum cloning, which is not allowed if we have linear evolution in quantum mechanics. Now, do you want me to explain why this is not? I mean, it's just a matter of 2 lines, right? So this space-time has a property that you throw something in, and then the black hole, together with Hawking radiation, produces a second copy. It doesn't matter what you throw in, you will always get a second copy, right? So it seems like you start with state psi, and it evolves into this type of state. And you can check that this type of time evolution, if this evolution is true for any state psi, this is inconsistent with linearity in quantum mechanics. It's, the one way to check it is to see what happens to the state 0. It goes to 0, 0. The state 1 goes to 1, 1. But so this is what you get by the rule, right? Now let's see what we should write down for the state 0 plus 1 divided by square root of 2. Now, if you take this state, there are two ways you can calculate what will happen to it. One is by applying the rule. The rule will tell you that you should get, 2 copies of the state. But linearity of quantum mechanics will tell you that if you superimpose this state and that state, that's what we did, you should get the superposition of these final states. So linearity of quantum mechanics is telling us that we should get this state. And you can check that the two are not the same because of the cross terms. It's actually quite obvious, right? I mean, this equation is not linear, right? It's just quadratic in some sense. So it's not. So this will be a problem with linearity of quantum mechanics. And here it becomes clear what is the difference with the sun. Somebody asked the question, why don't we worry about the interior of the sun? Well, in the interior of the sun, you don't have this copy. The interior of the sun, once this qubit falls into the sun, it gets destroyed, right? It gets scrambled with the rest of the particles in the sun, and eventually the quantum information can be emitted into the radiation coming from the sun. But here, because of the geometry, it is possible to draw the slice where this guy has not yet been destroyed by the singularity, it's still present, and at the same time, it has been emitted in the form of inside the radiation. You cannot draw this diagram for a star. Yes. Say again, please.
I mean, since all the observers are outside the horizon, does it matter if something is that is
Okay, I guess this will be the next step. Let me try to. So indeed, I mean, one proposal about to resolve this paradox goes under the name of black hole complementarity. Which was proposed by Larus and Susskind and Toft. And now I think there maybe, I don't know if there's a single interpretation of what we mean by this. One interpretation might be the following. Is there any observer who can actually detect both of these particles? Well, naively, it seems that that's not possible because one is far away, the other is inside the horizon. So naively, it seems that if you decide to check this guy, you will not be able to find that one and vice versa. So just a second. So one idea is that no one, there is cloning, right? There is some sort of cloning, but no one can detect it. So maybe it's operationally meaningless. Or maybe, I don't know if it's a correct statement. Let me not write here. So no one can detect this cloning, and perhaps the question of what is the quantum state on this slice is operationally meaningless because there is no observer who can actually do anything with the entire quantum state. And sometimes, I don't know if it's, everybody agrees with this, but another interpretation perhaps is that the Hilbert space cannot be factorized into the interior times the exterior. So in quantum field theory, if you have a horizon, let's say if you look at Minkowski space and you draw these light cones, you can certainly, well, up to some UV subtleties, you can factorize the Hilbert space into the right part and the left part, right? And you can think of the full Hilbert space as being factorized. This is not technically correct because of the UV, but morally speaking, it's correct. But in quantum gravity, this may not be true, right? In that case, this copy here may not be independent of that copy, right? That would be the idea. We will come to it later, and I guess Larus will explain in more detail in his lecture. So I don't want to say a lot about it now. So this will be the idea that yes, okay, there is some sort of cloning, but nobody can see it, so that's not a problem. Was there a question?
Yeah. So to argue for this cloning, you have to choose the moment of time, so the slice. You have to choose minimal. So you have to choose it after the half-life time of the black hole, right? So, but after the half-life time of the black hole, the entanglement entropy is so strong that you cannot trust geometrical description.
Sorry, why do you say that? Why do you say that if the entanglement is very large, you cannot trust geometric description?
Yeah, the entanglement is large because you are after half-life time of the black hole. But in this case, you can no longer. So the background you can no longer describe by a classical field.
Why do you say that? What is the precise argument?
So this you can check in simple toy models.
Yeah, but well, it would be great if you could find a reason why you cannot trust it. But that's a problem. That it seems like you should be. It seems like you should be able to trust it. That's why they're called nice slices, right? Because they have low curvature everywhere. And usually we think that effective field theory breaks down when there are high curvatures or high energies or something like that. Now, what is the precise reason that you claim that this slice is not reliable? You mentioned entanglement, right? But
but you can have in much simpler field theories, you can have states where the approximation for a classical field is not good, and this is typically the case if. The fact that the entanglement entropy is large is telling you is a signal that you cannot trust that the approximation for classical field.
Okay, first of all, I'm not sure if you are talking about classical versus semi-classical. Are you talking about, for example, whether the occupation levels of the particles are large or small?
I mean that you can trust geometrical description, so that G mu is a classical.
No, right, good. So I don't think you can. I mean, I don't know how to do that. If you know that, I mean, I don't think anybody has done that. You're claiming that if you calculate the variance of G mu nu over these long time scales, that because of the entanglement, the entanglement indicates that the variance will be large, right?
Yes, but
how do you prove? How do you prove that?
I have not seen this, but you can do this in much simpler field theory. So in field theory, this is
yeah, maybe, but here you can. I mean, it would be great if you can do that, but I don't know. I'm not aware of any computation of this type. Maybe you can tell me during the break, but I don't think that this is a standard thing, right? Maybe you have done it, but because again, the argument is that if you calculate the classical geometry on this slice, it has low curvatures everywhere. So why would this quantum effect that you are talking about, become important? You mentioned the entanglement, and you mentioned some other toy models, right? But I'm not sure if these toy models are exactly the same as this one.
Yeah, but that's a property. So if you just take any field theory, for example, electromagnetism, you can have states where the approximation to a classical field is
I agree with that.
no longer good.
Yeah, of course.
So,
But the fact that it doesn't work in those states doesn't mean that it doesn't work in this state. I mean, what's the connection?
yeah, but why should, after half-life time, why the state should be such that you can still trust?
Because in GR, in semi-classical GR, we have some conditions that we think we understand about when the naive semi-classical description will break down, right? For example, if you have very high energy densities, if you have large curvatures, and so on and so forth, right? So there's a set of criteria that we know. Now, those criteria are not violated in this geometry. Entanglement is not part of the criteria, as far as I know, right? So, I mean, when you study effective field theory and you study which operators are important, which processes are important at low energies, usually you don't talk about entanglement, right?
Yeah, maybe go ahead. I don't want
Okay.
to go into your lecture for a second.
Okay.
I mean, on the same topic, so I mean, you could just say that you don't know what happens. So as I said earlier, so after the half-lifetime, you know you have an object of the half the energy, but who tells you that this is still a black hole?
You mean like some sort of remnant of
whatever. I mean, I'm not so saying I can prove that this happens, but as long as you can.
I mean, if you, I think if you had if there was a specific mechanism that would stop the Hawking evaporation at m/2, that would be very interesting, right? But
But I mean, it just seems that no one can compute what happens after m/2. So there's no computation happening.
no, you mean for the classical geometry? You mean in the classical geometry?
Yeah, but that's already the assumption that you put in that you keep a classical geometry.
You're saying that you're saying that the geometry will become highly quantum at that point, or something. Yeah, okay. For example, the firewall proposal is something of that sort, right? The firewall proposal is saying that after the half point, there's no longer a black hole, right? It's no longer a black hole. Now, I don't know if you can really do a reliable computation by taking into account the back reaction of T mu near the horizon, and I'm not sure if it's completely trustworthy. So, in principle.
I'm not sure either, but I'm just saying it could be. And as long as it could be, it's a strong claim to say that you still have the geometry and the
Why is the strong claim? I mean, this is a geometry with extremely low curvature everywhere, right? And there's a very small quantum effect that is slowly decreasing the size, right? It's really, really slow, this effect. So you're telling me you cannot trust it at all, this estimate that you're making, right? But you have to give me a reason, I think, right?
But the reason is that you have a strong back reaction.
Oh, sorry, what is a strong back reaction?
I don't know. May I say something? I think that it might be helpful if we think of an evaporating piece of coal and to make the analogous claim that after half of it has evaporated, something drastically changes the evaporation process and it turns into, I don't know, something. How do you know that that doesn't happen? Well, I don't know. How do I know that the moon isn't made out of cheese if I think you know, right? It's what we do is we use the most conservative assumption until we have a strong reason not to do so. We don't just say, we throw our hands up in the air and say, miracles happen in the middle of nowhere. There are good reasons to believe that something drastic might actually happen. But you have to make an argument for it, as Kyriakos says. You have to have a reason. It has to be a good specific reason where you run into some conflict with some other principle, perhaps.
Okay, so I have to stop, I guess, right? Yeah. So before I close with complementarity, because I'm not going to talk about the firewall now, I guess Lars will mention a few. There must be some consistency conditions here that you cannot You have to check that you cannot do experiments where this particle hovers near the horizon and then you collect it there and you see it again. There are some estimates in the timescales you have to be careful about. But also this idea of complementarity, it identifies the interior with exterior, so it's not obvious whether it is consistent with locality in effective field theory. Okay, you have some arguments, I guess. There were some arguments also by Amsterdam about this, and I will try to argue tomorrow that it may be compatible by introducing some other ideas. And of course, we don't have a mathematical formalism, right? This is just it's a principle. It's not yet a mathematical framework. So tomorrow I will continue. I haven't finished what I want to say, but I will continue with explaining why these ideas about something happening after the half point may actually be important. And I will do that by reviewing the strong subadditivity paradox, also called the firewall paradox. And I think I will try to spend half an hour on that, and then I will move on to the paradox in ADS-50. Thanks.
Okay, we already had a lot of discussion and it's so late, but maybe there's after 1 hour.
I have a small question about your calculation with typical state.
Yes.
So you said that the corrections you get in expectation values are small. But is that true even if you take some operators which act on more than half?
Yes. Well, yes. What do you mean by that? I mean.
Something like take a bunch of B's, but then their number is more than half.
Okay. Are you going to divide the result by the norm of this big guy or not? If you divide by the norm, then the theorem is true. It's irrelevant. It's irrelevant. It's relevant.
But in absolute value, you would still be able to sort of detect.
No, you'll not be able to detect. No. Why do you think you'll be able to detect?
Well, it's just my intuition.
I mean, any observable, even if it's complicated, you can imagine that you normalize it so that its eigenvalues are order 1. Why not? Can't you do that?
No, you certainly can. I was thinking that my intuition is that if your subsystem is small enough compared to the whole, it looks thermal, but if it becomes larger, then...
but to do that, you need to calculate the density matrix of that big thing, right?
Sure,
but computing a density matrix is much more complicated than computing the expectation value of one observable, right?
Sure, but then you could find the proper observable which detects that you're
if it's state dependent, yes. If you align the observable, if you already know the state and you align the observable in a clever way, as we saw before, you can do that. But if you don't know the state, I don't think you can do this by measuring the one observable. I may be wrong, but I don't think you can do that. Maybe we can try it.